Good morning, everyone. Today, I have the privilege of guiding you through a fascinating journey into the heart of the enzymology, focusing on one of its cornerstone concepts, the Michaelis-Menten equation. The equation is not just a formula. It's a window into understanding how enzymes, these catalysts of life, interact with substrates to facilitate biological reactions. Let's start. Hi guys, today we will going to explore the derivation of the Michaelis-Menten equation, or a cornerstone in understanding enzyme kinetics. This equation helps us understanding how changes in substrate concentration affect the rate of an enzyme catalyzed reaction. Let's begin by looking at the basic reaction scheme involving an enzyme and its a substrate. Step first, reaction scheme. We start with an enzyme E binding to a substrate S to form an enzyme substrate complex ES. Can you see it? Complex. This complex can either break down into E and S process to form the product and enzyme. So this process is described by 3-rate constant K1 for the formation of ES, constant of rate, and then K-1 for the dissociation back to E and S, and K2 for the conversion of ES to ENP product. So finally, we can write down this reaction E plus S, ES, E plus P. Step 2, steady state assumption. In the steady state, the formation rate of ES equals its breakdown rate, meaning the concentration of ES remains constant over the time. Thus, we write the steady state condition as dES divide dt is equal 0, leading to the equation of K1 E and S equal K-1 plus K2 and ES. To simplify, we rearrange this equation to solve for ES, the concentration of enzyme substrate complex. Here, we introduce the Michaelis constant Km. Km defined as Km is a measure of the substrate concentration at which the reaction rate is half of its maximum value. So I can explain and write ES equal K1 E and S divide K-1 plus K2. And then Km equal K-1 plus K2 divide K1. So we can put in this equation inside this equation, right? Step 4, defining Vmax. The maximum velocity Vmax occurs when all enzyme molecules are bound to substrate and the reaction is proceeding at its fastest possible rate. Mathematically, Vmax is defined as K2 E total, where E total is the total enzyme concentration. Combining all we discussed, we arrived at the Michaelis-Menten equation. The initial reaction rate is V0, is given by V0 equal Vmax S divide Km plus S. This equation describes how the reaction rate varies with substrate concentration, highlighting the hyperbolic relationship between these two variables. In summary, we have walked through the derivation of the Michaelis-Menten equation, highlighting the key laws of Km and Vmax in enzyme kinetics. Understanding this equation allows us to predict how changes in substrate concentration influence the rate of an enzyme catalyzed reaction. Thank you for joining me in this exploration. Thank you. Bye.